Hello, welcome to the second session of Computational Electromagnetics. We are going to see the numerical solution of the Maxwell equations for electromagnetics. Last session, the first one, we first presented the applications and in fact commented Maxwell equations that are those that are being solved. Involved magnetic flow, as we will see, and also the electric field, and the two are always coupled, even if we reduce the equations for 2D or 1D. So in this case we have the electric fields and the magnetic fields and the magnetic flow and the electric flow. And these fluxes, in fact, they are related to the fields, to the constitutive equations. We see that even in 1D, they will be coupled, and they have this wave-like behavior that we also deduce with that speed. That would be the speed of light in case that we use the permeability and permeability in the empty space. Then we'll revisit that, but what is the message here to keep is that electric and magnetic fields, they are both coupled. In this case, with the derivatives with respect to y and derivatives with respect to z are both neglected, we end up with a system with E2H3 transverse to the direction of propagation. That would be the x direction, as we saw in that small movie. So the two of them will be coupled, in this case with the transverse electric, and we have the transverse magnetic. Right? They're called transverse electric and magnetic because the corresponding in 2D would have E1, E2. Okay, that it would be on the plane for H3, which will be orthogonal to the 2. Okay, and that's these that yield to these equations, and these last three that give rise to this transverse magnetic. Okay, so solving one or the other, it's in fact giving the same solutions, but always coupled. So we saw the how the analytical solution may look, and we look at the scattering problem, okay, where we are going to deal with a direct problem, that is having an obstacle and deducing how is the field of the scattered problem. The inverse, interesting from an engineering point of view, is deducing the shape of that obstacle from reading the scattered field that we have, okay, from the object. Right, so we first had a quick look on what we are solving. So we know that E and H, okay, the two magnetic and electrical fields, they are the solution in the space where we are with the material properties. It will be by the permeability and the permittivity epsilon, and in the empty space, okay, the incident wave, that assuming that is coming from the empty space. These equations are also valid for using the epsilon sub 0 and mu sub 0. Okay, so because these quantities are known and we assume that we know the incident fields, what we have is a system of equations with an additional source term. We deduce where this is coming from, which in fact is just solving for the scattered field, right? So that's our known in the system. We may also solve for the total field as well, but in this case, that would be what we would be measuring. In fact, what we see is the total field, but we know that the sum of the two gives us the total field. So we can either solve for the scatter or for the total. If we solve for the scatter, then we have this additional source term, okay, and that gives to the equations that we will solve for the scattering problem. So we need to know which boundary conditions. Okay, we know the equations that must be satisfied for each point, and the boundary conditions. So it depends on the material or the interface that we are dealing with. That is electromagnetic equations, which in fact some of them they are filtered. Okay, due to the boundary conditions that we have for our domain, or the presence of an interface that would be the glass. Okay, the glazing that we have it for that car. Then which type of boundary conditions? So we need, for instance, in this case, if there's continuity, okay, for the right and left sides, what we are saying here is everything that is orthogonal to the normal, it has continuity on the left and right side. So in this case, would be okay on the right and on the left the same field, and that would be given by this condition here. We may have the same situation for the right and left magnetic field, or we may have for the fluxes, continuity of the fluxes. There's an alternative, okay, in position that's saying that our fluxes, okay, on the left and on the right, or the other way around, because we have L and R here. It doesn't matter, it depends how we look at them. But in fact, the two of them are going to be imposed by their material properties. Each one may be different, and we have an interface. So in fact, what we are imposing is that the fluxes on the left and on the right should be equal. So there is continuity of the fluxes with respect to the electric or the magnetic field, and in this case, what we're imposing is that the field should be equal on the left and on the right. So in the presence of an interface. Okay, for a perfect electric conductor, in fact, what we impose is that it prevents, okay, so the conductivity through it would be preventing the electric field, okay, tangential to the interface that we have in here. Okay, so that we have that on that material, in the perfect electric material, there would be no tangential electric field in that case, but the normal might be different from zero. Instead, from the normal direction, if this is n, then we will have that along h, okay, this should be equals to zero. So where this come from, in order to deduce these boundary conditions, you need to consider the integral form of Maxwell equations. The integral form of Maxwell equations is nothing else than, in fact, having the integral, the derivative of our b, okay, we are considering a surface, okay, surrounded by a given integral, okay, around the boundary of that surface. So if we integrate the time derivative of our, in this case, our magnetic flux, it's equal, okay, that's the integral form, it's equal to the integral on the boundary of our surface of our electric field, in this case, so coupling these two terms, right? So this is the integral form, and if you consider, okay, so any arbitrary surface, okay, with a fixed boundary, so it says that the time derivative along this surface it's equal, and if we use Stokes' integral theorem, so the integral along the boundary would be the integral along the surface of the rotational. We have a minus here when coupling the magnetic and the electric field. Okay, so we have, in this case, using Stokes' integral theorems, that the integral along the boundary of the electric field is equal to the integral on the surface of the rotational of that same field, with the same minus here and the integral on the s. Since arbitrary is the surface is arbitrary, then we have our equations that must be preserved for each point. Okay, that would be like the strong form. Okay, that's the one that we use. The one coupling the electric flux D and the magnetic field H here is exactly similar with a plus, and also considering some charges, and we get the other strong form, the other one that we also considered at the beginning. That would be our electric fluxes equal to the rotational of our magnetic field, and potentially also some charges that we consider due to the conductivity. Right, so this is the integral form, and in order to consider that boundary condition, what we need to do is consider a surface that goes through the boundary. Okay, so something like that, and we consider a boundary like this, and we're doing this integral as this height dn goes to 0. Okay, and then we have the condition inside here. This is our normal vector. And considering the surface, and because the time derivative of b is not changing, if we change this width of this integral, so you end up by having the rotational of E should be equals to 0 in a perfectly dielectric, perfectly conducting dielectric, then we will have that this should be equal to 0, and from going dn going to 0, then we have that our tangential part, we consider in general in 3D, that may be an integral in any direction, so we have that the rotational or the vector product of n by e, okay, this should be equals to 0. Okay, since for the coupling that we have for the transverse electric and the transverse magnetic, okay, this also ends up by imposing a condition into the orthogonal direction of this field. Okay, so the tangential field here must be equals to 0, and the normal component with respect to the magnetic field should be equals to 0. The two, we saw that when it's propagating, we had this E1, E2, okay, for the transverse electric mode, okay, and the direction of propagation was along the three directions, so we'll have something like that. Okay, the transmagnetic is replacing E by H, in this case an H by E, something very similar. Okay, so if it's being posed tangential is equal to 0, okay, also the normal they are going to be equals to 0. So this is the boundary conditions for a perfect electric conductor as we may have in here. So this is the explanation. So you need to consider the integral form of Maxwell's equations. That is what we have just written now. And this idea of the proof that we have given. Then, if our domain, as usually happens, it's unbounded, so we usually consider electromagnetic problems in the outer space. So this is coming an income wave coming from the infinite. So we want to model our domain as if we have unbounded. Due to computational cost, of course, we want to reduce our domain which we are going to discretize. So reducing the number of finite elements, for instance, that we will have. So we are interested in having a small domain, but simulating as if there would be infinite domain. So the condition that we want to simulate is that our waves that are being scattered by the object, they are not reflected by the boundary, as if this boundary would not exist. So the non-existence of this boundary, one way of simulating that would be using the absorbing boundary condition. I mean, we are going to use a given absorption of the electromagnetic waves in order to not to absorb too much, so that is not going to affect our scattered field here, but also not having no absorption at all, that then we would have a reflection at the boundary. So this absorbing boundary condition, ABC, that we use through a PML. PML is a perfect matching layer, so we have a layer that perfectly matches the infinite condition. There's different ways of simulating this infinite-like boundary. One way is this PML. So we are going to have some artificial conductivity in here. So we have the perfect matching layer in here outside of our domain, and we're going to introduce some conductivity. Okay, some conductivity for this quadrilateral. This boundary is omega 1. We're going to have some conductivity along x direction. So the waves going along this direction, because we don't want that waves along the y direction here are being absorbed. Okay, so they should be constant along this y direction here, and the same on these two domains, the upper and lower side of this domain. So we have omega 2 with some conductivity that are going to be absorbing our waves along this y direction, but nothing along the x. So we have these conditions for the domains omega 1 and omega 2, and what these parameters, we have a parameter n, we have a parameter b, and this b is the width. In fact, b minus this small b is the width of this layer, we want to use a extra layer that is not too thick, neither, also for reducing our computational cost. And if you look at the expressions that we have, this extra layer, what is, for instance, in this omega 1 that we had here, what is doing is that our conductivity is increasing along this direction. Okay, so we have this profile of our conductivity, okay, along the x direction, okay, because we have sigma by b minus b. This is the distance we have as b, and this is our capital B. So we have this x minus b and to the power of n. For n equal 1, we have this linear behavior, but we can impose other quadratic behavior along this direction. And so there's some calibration of these parameters, so how the width of this extra layer that we have. Here we have our domain of interest and with our obstacle, and so we need, depending on the size of the obstacle, we'll have different sizes and different ends. So there is a little bit of tweaking for this perfect matching layer, but for some parameters it will work. This absorption, okay, we are going to use this absorption in the case of the we have our H1 and H2, so the transverse magnetic, and we have transverse magnetic mode that we have. So into this, so we'll have in our X and Y, we're going to have H1, H2, and we are going to have our E3. Okay, that's how we would simulate. So we have absorption, and we are going to have absorption for the E3, and we decompose our third mode into two quantities. Okay, one that is going to be absorbed, okay, along this x direction, okay, as we go through that domain, but the E3y is not going to be absorbed along this domain. So okay, this is going to be affected by sigma x, and this is going to be affected by our sigma y, different conductivities. This conductivity is not real, is some artificial artifact that we do in order to have the right non-reflection condition by this boundary, okay, that we have in here. Right, so we decompose in that manner, and we write our equations, for instance, in 2D. That's what is done here. Okay, so we have the first set of equations. This is exactly what we have in that form. Remember that what our equation for h is mu by the derivative of h with respect to time equals to minus the rotational of E, okay, which can be written, okay, as derivative of u with respect to time plus derivative of fk with respect to xk. So if we look what is derived with respect to x1 in 2D, okay, we are now looking into the equations in 2D, okay, with a summation here, we look what would be this rotational writing as the sum on that side, and we look at what would be with respect to x1, okay, we would then have a second component, for instance, with the derivative in the second component of the H3. So what we know is that it's going to be an, in this case, with the f of u, we're going to have the E3 in here, okay, for the second derivative that we're going to use as u, okay, containing our H1, H2 multiplied by mu and our E3. Right, we have the total components in 3D, then we will have like an epsilon E3. Okay, and we need to couple these equations with those equations that we have also for the electric field. Okay, and we couple and we write in that manner. So we know this term, what we will have with respect to also the x1 here will be the similar thing, but with respect to the h3 that we would include. So we know this set of equations. This is the standard equations that we'll have for the transverse magnetic. right? And this is what is derived with respect to x1 and what is derived with respect to x2. And no derivatives with respect to x3 because this is, in this case of the transverse magnetic, with into d, so means that this is no derivative with respect to z. And what we have here, in fact, is sigma as a source. In the second component, we have an absorption, okay, that we have with respect to H2 as well. They're going to be affected also by the conductivity and artificial absorption we have for H1 and H2. And this will be H1, H2, and we have here is one affecting the x plus another term affecting the x here, the y, sorry. Oops, this doesn't go back. So we have this y. So if you look at this expression, in fact, and epsilon 3, bear in mind that we have decomposed the total third component into an x plus y. Okay, so here we have x plus y, and the x by sigma y is cancelled by this term. So we have exactly also this third condition, we have this term here. But of course, this decomposition is not unique. We have different manners of decomposing that, and we have such a decomposition that we impose, okay, that there is no, for the epsilon 3 y, there is no derivative with respect to x. Okay, so there is no derivative with respect to x on this epsilon 3 y's on the equation. Okay, and the same we do the derivative with respect to y. This is the one that is being absorbed on the top in here, the epsilon 3 y, so it should be constant. Okay, so no derivative with respect to x, and the same here for the epsilon 3 x. There is no derivative with respect to y. So we have in total, by using this decomposition, in order to have different absorptions depending on the boundary how it's oriented, we end up by having an extra cost of an additional equation. Right? So we decompose, we have an extra equation. And this is happening, so one extra equation in 2D, but if we work in 3D, then we will have, of course, then boundaries. We have boundaries with respect to x, y, but with respect to also along the three directions. So we have one extra, okay, for each one of the components that we have, E1, E2, E3. So we have to decompose also as well, okay, the other right, the other fields where we'll have x and y. So the reciprocals also the compositions, because we have different directions, okay, not only x and y, and you end up having in total 6 extra equations. So it has a cost in 3D by considering a box. So this is a bounding box of our domain, which can be Cartesian, so we can do this decomposition, but we need to do it for all the variables in all the directions. Okay. So with that, it is just more complicated. Okay, but it works well if it's well tuned. We will see some examples of this absorption, how it it really improves the solution. So let's see some applications that we have, for instance, of the scattering problem, and also to give some numbers, some practical numbers on how does it work in the case of a radar. You have an emission, and you have a target, and then you receive. Okay, some of the waves go through. Go forward past the object, and others are scattered and then are being received. So how much you receive, it depends on different parameters. Of course, it depends on the distance, it depends on the emission, how much power you send, but the most important, it depends on the obstacle. So there's a geometrical parameter that states how much of this power that we send is going to be received. And so looking at different how all these is dependent, so these factors that we have, there is one factor, so how much is going to be received will also depend on the antenna that we have, how much we are able also to detect from the antenna, besides of how much we are going to send. Okay, so working that into numbers, we have this parameter that says how much of the power that is going to be scattered by a given power that you send. Okay, so you send this power and you receive, and of course it depends, okay, on the distance. Okay, and this factor, okay, this takes into account the fact that all is being sent in all possible directions. This factor is how much reflection an object sends. Okay, so if a factor have a larger sigma, this is called the radar cross section, and this radar cross section, how much is being received. So if this is a larger parameter, you will receive a larger amount of power. And if you much closer to it, so R would be smaller, and then so would be a fraction of that you can receive. So depending on your distance, and working that into the field, not in terms of power. Okay, the power is a function of the square of the field. So in terms of field, so you will have a fraction of the power to the power of 2 of the fields, right? So you have interest depending on your application. You have interest on have a small radar cross section, so it will be very undetected because your power that's being sent is much smaller, so it will be much harder to detect. But sometimes you want really that you are able to be detected, so you might be interested in having a sigma maybe a little bit larger, because there's, depending on the geometry of the object, there's big difference in the ratios. You measure this fraction in decibels, which is the logarithm of this sigma. Okay, and you multiply by 10, and this is then called decibels. Okay. This has the units, okay, as we see here, of square length. Okay, so it's measured in square meters, and you can measure that in decibels of square meters as the units, and there will be 10 times the logarithm of the radial cross section. And of course, this is a geometrical property, and these are maybe like the a reference of your length that you have. You have then how much you're going to receive. So this is how much you send. Okay, you transmit to your, now from the boat point of view. Okay, you have an antenna, and how much you're going to receive, it will depend on this geometrical parameter you have here of your object. Okay, and then of course, now if you are farther away, of course you're going to decrease your signaling. Okay, so you have these factors also. So if your antenna has a better gain, so then you will receive much more. Also depending on the wavelength, so smaller wavelengths have really harder to detect. Okay, so you want to have interest into send power into a larger wavelengths if possible, and of course your sigma, which is the object, also is going to affect this received power. So some reference numbers on how large is this radial cross section. Okay, so as you see, there's orders of magnitude in difference, and you may have insect with very low the units of these square meters. Okay, so has a little bit referred to the reference length that you have, this R that we have in sigma, but for to go larger for birds, but you may have really much larger for ground vehicle, armored, or for a ship, so may go to the 10 to the power of 4, 10 to the power of 5 for very big carriers. Right, so even around some of these intervals, for instance, in a carrier, you can play a little bit with your shape, okay, and have a smaller sigma as well. So how much you're going to scatter with respect to your size. So there is techniques, okay, how to make your more transparent with respect to electromagnetic waves, and this is a little bit less or more fashion airplanes, where you can say that an airplane is invisible. It really has very low radial cross section. Okay, when it's smaller than 1, that will be negative. Okay, so it means that your fraction with respect to your size is really small of the scattered power, and you can go even for even smaller. So these are called like phantom or invisible airplanes with these small radial cross sections. There's other more rudimentary techniques that you may think, like also not being perfectly transparent, but um, deviating what is your electromagnetic incident waves. Right. So there is material to compare with the material if they are absorbing, so with this conductivity but having a real physical meaning, and so etc. But also playing with the shape. So now let's go to the numerical solution. Why is that? So you can imagine that testing that this even before you have the actual prototype, you have interest in having a numerical solution, because playing with size matters. So you need big testing domains, and you need also, so this absorbing matching layer we had numerically, so you need to implement something if it's not in the open air. Otherwise, you need a testing facility on the open air. So instead of having this absorbing boundary from the electromagnetic perspective, right? So you have no scattered fields, and that simulates the infinite, as if that would be flying really in the open space. So this is not always possible depending on the object that you want to test. So you need testing facilities in the open air where you send and you receive, okay, and you see how much, and depending on the angle, you will have different perceptions. So the scattered field, it depends on your position. So for the radar cross section, you plot this quantity depending on the angle with respect to your object. Okay, you can do in one direction around the object, or you can do in 3D. Okay, playing with two angles. Right. So testing facilities are not cheap, as you can guess, but then you have the computational facility, and for that we are going to see at least how we can model that. So in order to have some analytical solutions, we know that these equations that we compose in that manner in a conservative form, in this case our f are linear, okay, because it depends linearly on h and e. We have the material parameters in them because u contains the material parameters in our time derivatives. So we have these A matrices, so it's linear with constant A matrices here. And this system in conservative form with these linear matrices, we can say something about them. We know that here the characteristic lines are important, although we have this factor which is a matrix. It's not like in the scalar case. Okay, whenever we work in the scalar case, we have the derivative of a given quantity with respect to time plus a given scalar by the derivative of u with respect to x, so equals to 0. This is the type of scalar equations that we have. So we knew that u, okay, does not change, okay, along lines, okay, with velocity a. Okay, these lines, okay, these are the characteristic lines. Okay, why? You know that if a would be our velocity, then we knew that the total time derivative of u, okay, with okay a quantity that moves along this velocity, okay, is the same as the equations that we have. Okay, so it means that along time, and if we have a quantity that moves according to this velocity a, okay, okay, the hypothetical velocity that we will have, then our u is constant along these lines. Okay, and this gives us some some knowledge about how our waves are going to behave. So if we have a given initial quantity u0, so we know that along this line this is not going to change. Okay, when we move our particles, as if our particles would move with this velocity. So that would be our u of t is just a translation along time, okay, of this profile. In our case, we have a matrix, so it's not exactly the same. It's a little bit more complicated because our u is multiplied by a matrix, and we have, okay, not derivative with respect to x, but a sum of u with respect to x. And what we can do is trying to work with a different, try to have diagonalize this system. Okay, we can work with another quantity that we can, okay, at least pre-multiply and work in terms of our z. Okay, so and with that, if we have a certain transformation, that we can have the inverse here. So if this is an inverse, so it means that our u may be equals to rz, and then have our equations. If r is constant, then write our equations of derivative with respect to z with respect to time plus ak multiplied by given also the r that we will have here by derivative of z with respect to xk. This may be different for each one of the r's that we have, or having one that is constant to all them. So if there's a possible diagonalization of these a's, okay, so if we have potential that diagonalization of our a's, it's equal to diagonal, then we can uncouple and analyze from that perspective for a given direction. The direction will not have any special meaning here, because it's it's an algebraic transformation that we do of our matrix. But we know that we have some given rotation, and we have some meaning r as a rotation, but maybe any transformation that we have. So we have transform our variable u into another set of variables that diagonalizes our system. So when that is done, and what we see from that matrix, in fact, is that one of the eigenvalues that we have for a is a 0. Okay, so one of the velocities where our conservative form has a scalar form will be for the one that has a 0 value for vector, 0 eigenvalue for a1. Then in that case, we can look into the scalar form and see in which directions our equations do not change. And we need also, so it's important to impose the characteristic equations. They have effects on which type of boundary conditions we can impose, because it tells us along which directions our variable is not going to change. So we need to take them also into account. We don't give much data about this decomposition or the form of the characteristic lines for the electromagnetic problem, for instance, in 2D. What we know, there will be 3 of them, okay, and because our matrices are 3 by 3 in 2D, so we have 3 characteristic lines, okay. And this, if we have, for instance, a perfect electric conductor, we know these are the boundary conditions, and we may need to impose also some extra conditions, okay. Ranking humanoid conditions, they impose also a balance of energy along the interface, okay. And so this, for instance, if we have an interface like with a left and a right, okay, and we look at the point here at the interface, so we have some characteristic lines that go to the right, others that go to the left, and there's one that is equal to 0, no velocity from these matrices that we have. So these three characteristics that we have, there's one that just remains here. Things are not changed, can remain unchanged at the interface for some combination of the fields E1 in the magnetic transfer magnetic mode for H1, H2, and E3. Okay, so the combination of them, there's not one of the variables because we do a transformation of the variable, the combination of them that does not change. And our boundary conditions should respect also these characteristic lines, or that quantities do not change at the boundary. So that's why we need really to take them into account. So these are type of looking at the type of analytical solutions that we have in electromagnetics, and if we look at the numerical solution, so we know in this case for the transverse magnetic we should have divergence-free conditions. Okay, at the continuous level we know that these are divergence-free. What may happen at the discrete level, we don't explicitly impose that, for instance, that the divergence of H is equal to 0. Working into this, so would be that the 2D divergence of H should be equal to 0. So we see that maybe a drift. Okay, for instance, in this wave, we see that there's a shift. It's not constant, but is the delay between one and the other. So we see, for instance, in here, okay, how H2 is evolving with respect to E3. So there's a small shift between the two. So there's ways of projecting. If we do long time evolutions of projecting our fields to the divergence free, okay, or having like the shift is preserved between the three, right? So these spurious fields is a numerical artifact due to the discretization that we are using and the weak form that we are going to use in these equations. Okay, and one way is to use an approximation, so to discretize our field, which is already okay respects when we say the curl diff system, that it respects from construction this divergence free condition that we have here. Okay, or if we have for instance in a steady solution, would mean, so this curl discretization would mean that it's already preserving this curl free condition that we have here if we don't have any time variation. We would have depending on the boundary. So one way of testing if the numerical solution works would be, for instance, working with a radar cross-section. Radar cross-section in theory is checking how the ratio of our scattered versus the incident and the square of them is responding for one of the fields if we work in 2D, and we see how this behaves as R goes to infinite. So we cannot do this limit in the computational model, but we can work with a curved C and do the integral of this curve and see how it behaves as R goes to infinite. Okay, so we can do a projection from the near field to the far field. Okay, as far as this C encloses, so we're going to an approximation of the radar cross section by looking at this integral. Okay, even if we have a bounded domain. This has been tested, okay, and we can consider classical methods like finite difference. So the derivatives, this is in time, this is very often used. In a space, you can still do that, so it's cheap because your mesh, as we know, has constant discretization, so it's cheap to use. All the elements are equal, or you can use a finite element so that you discretize with arbitrary geometry or with a finite volume, okay, which is used in electromagnetics. You will see some of the finite volume in acoustics, okay, in the next session. Then we can have more advanced strategies because geometry matters, and using standard finite elements, your description of the geometry may be inaccurate. Even if you go for higher degree, may be expensive and inaccurate. So it means that continuity that you impose between elements may not be beneficial if your field in fact has discontinuities. Okay, so you have mesh-free methods where you don't have the mesh generation, although you need a mesh to integrate. Okay, but at least you need to generate a mesh to describe the geometry. In discontinuous galaxy, where you have discontinuity of your field. Okay, so for each node, you may have a quantity on the left and a quantity on the right. Okay, so this maybe we accept discontinuities on your field, and you solve locally for each element. Okay, and you just solve very cheaply inside each element, and then you enforce in a weak form discontinuity between elements. So this discontinuous galaxy works well when you have in fact discontinuities. Okay, so you can impose, and also allows when you have very large degree inside one element. You really are not much bothered about the degree inside one element because you have just to solve a local problem within each element. Okay, so very work well with high degrees of interpolation. And this is a NURBS enhanced, which was developed specifically for this type of problems where the boundary really matters. We will see some of these examples, so I'll explain right now these in detail better with the images that we will see. So this is a radar cross-section. As I said, you have an incident wave in here, and you measure which is your scattered wave for different angles. So that would be in the center. You have is where your scattered is higher, but as you move, okay, so the energy that it's being scattered, or the scattered field may decrease for some angles. When you go to pi 4, it will be like 45 degrees when you have still some values, but when you go at the back, it's much lower than when you have at the front. Okay, and you have some analytical solutions for very regular shapes like this circle, and here has been used this NFM, NURBS enhanced. You use standard, or in fact in this case DG, discontinuous galaxy. You see that inside one element it's not linear, so you have a high degree within one element. You may also have discontinuities, okay, within the element. This is not the case because it's continuous. And you have also the absorption, so there's a perfect matching layer around, so you see that the waves they diminish at the boundary, but avoiding any scatter. So it's going not to affect the scattered field that you have inside this domain. That is where you're measuring, and when you're doing this integral, okay, on a closed in a closed curve around this obstacle. So it really matches the analytical and the one done with the NURBS enhanced. Why it's NURBS enhanced? Because as you see, it is an element with the straight lines, but there, in order to describe the boundary of the geometry, you really use a NURB. A NURB is not a polynomial; it's a fraction. It's non-rational. It's called NURB is non-rational uniform B-spline, non-uniform rational B-spline, and it's rational because it's a fraction of polynomials, and in fact it's not exactly polynomials but a B-spline. It's a blended interpolations of polynomials at the numerator and the denominator. And it's non-uniform because this blending you do it in a non-uniform manner. In that way you are able to capture exactly the geometry of the circle. Right, so this is what you can get by enhancing the finite element with these NURBS, something really close to the exact solution. Then you can refine your mesh, and still, even if it's a little bit for higher frequency, you need to remesh with a little bit more elements in order to capture higher frequencies that you have here. And for the radar cross section, you see that it's not as smooth as what for the lower frequency, but still you're able to capture. So really nearly going on the top of the analytical solution. And that's thanks to the, in fact, approximating the geometry. So in electromagnetics, geometry matters, or how we saw that in the applications, how it's scattered the field. You see a profile of this higher frequency. So in fact, you have interest in order to have one element that is able to capture all these wavelengths, so to you all these wavelengths, all these oscillations. So with these much smaller wavelengths, then you need smaller triangles, right? So that's why you needed this more finer mesh. And then you can do that in 2D. You can do also for when you have not a perfect conductor, but when you have some interface on two different materials, and also there's an analytical solution for that. And for these wavelengths, you see that with very few elements, you are able to capture the radar cross section. A way of verifying the solution, the numerical solution. Then, because shape matters, when you have a mesh, you're interested also to capture, in fact, the real geometry. This is like the cut of an airplane, and when you go from the cut to your actual computational mesh, you have interest in preserving the smoothness of this geometry, right? So you have different profiles, and in fact, different profiles, they have very different aerodynamics properties, and you want that your mesh is as close to that, not only for aerodynamics but also for electromagnetics, right? And the lifting that you will have and the drag will depend on that, but also how your scattered electromagnetic field are going to be. So you see one of these profiles of the wings, and so if you are not able to capture exactly this geometry, it's non-linear. So if you just use FEM, of course you're going to be very inaccurate, okay, for this radar cross section. And even with a high frequency, with one element with a degree that is high enough, then you are able to get close to the analytical. It's not analytical in this case, a reference solution computed with a very, very fine mesh, much finer than this one, and is taken as the reference solution. And you compare that with what FEM is doing, which is a little bit inaccurate. So you have that for profiles in 2D of airplanes, where in fact you don't need the convexity, okay, depending on the scatterization that you may have. If you look at some of the elements that you have here, you may have some non-convex shapes, or even in some cases, if you do that with finite elements, you are forced to use an adaptive mesh in order to capture these shapes. But with this FEM, you don't need to refine up to that level, right? Because here, for instance, you have this weird shape that you can capture with NURBS, okay, with a high degree of nerve, and because they are non-uniform, you can do things like that. So the actual scattered field, how it looks, okay, from those profiles. So you perceive the smoothness of that, and with a spectral reference solution, you can get as close as nearly as these reference solutions. And even you have some details where you can compute your solution, even you have these kinks here on the profile of the geometry. Then actually you have antennas in the real airplanes, and you are interested in also capturing how this is going to affect my my sigma, my radar cross section of this object, of the airplane. Is this really necessary, or shall I remove it? How it's going to affect from the electromagnetic point of view. So you look at this object and you see that it creates some secondary waves, okay, and it has an effect. And you can do that, okay, thanks to that you have this enhancing. Otherwise, with finite elements, you would need to refine very closely here to get something meaningful. and some details of this refinement that is being done here with just a few elements. Here there's some conditions for this NFM, that is the visibility of those elements. Of course, they don't need to overlap or cross your domain in order to work well, but this is a minor requirement compared to the course that you will need with a refinement for a finite element mesh. Then you can do that also in 3D for different wavelengths or for different directions of your scattered field. So you can play with different angles, okay, in here. And with a radar cross-section with different, of course, in 3D, so you need to look at the three components of your electric field as well, right? And that you can do also extend also for the absorbing PML. Okay, you need to absorb your boundaries and look that is absorbed on that direction, but also on this direction and on that direction, right? And that, so you may need a given amount of the width of your PML, but it works, and that decreases really the effect of the boundary. Then you can, things that have been done so far is using different discretization for time and space. So this means finite elements in space and in time with finite difference, okay? And you can have finite difference for both in space and time. This is very inaccurate, but it's very cheap, okay? And for depending on what you want, that may be good enough, okay? And even for helicopters, okay? So you have the blades, and even for those cases, you may use finite difference, very cheap even for helicopter. But if you want to have an idea of the amount of scattering, but as you may have guessed, things can be improved regarding to space, and there's even finite elements in time. You can also do that and have a weighted form in time also. So this is more some details of the geometry. You can also work with finite volumes. You will see what they mean for those that you don't know what I'm referring to, but you will see that in detail for the next sessions applied to acoustics. And of course, then because your boundary, you can also use smooth surface description, like here, and then you can work, so the difference if you use a finite elements, so they are piecewise linear, and instead if you have with piecewise higher degree, and you can impose even the continuity. Okay, I'm working with C1 elements, and with that, of course, has an effect on your actual solutions. Okay. So this is still some challenge. So there's people working on the meshes, because meshing this, okay, what the CAD people have is a mesh of the surface, but of course they don't have a mesh of the domain, okay, of the 3D. So there's a challenge on adapting your mesh to that surface or one of the boundaries, right? So this is future work which has been a big breakthroughs in the last years, okay, with respect to the mesh and trying to solve the problems also for those detailed geometries. Right, so even for those cases in 3D where we're able to do a 3D with a real smooth surface, so hopefully yes, it's just a matter of getting the right enhancement with respect to those detailed geometry without the need of going very refined meshes in here. The visibility condition is more complicated for those cases, right? So this is like what has been done and challenges that we have. With that, the electromagnetics sessions is finished. So many thanks for your attention.